Honors Algebra 2 Pre-Calculus. We're doing 10.3 in Pre-Calc, which is ellipses. So the last topic in this section, we're going to talk about the eccentricity of an ellipse. So the eccentricity of an ellipse is given by E equals C over A. For all ellipses, E is a value between 0 and 1 exclusively. So C over A can't be 1 because if C and A were 1, essentially that would mean that B has to be 0. So if you think about it this way, so just to walk you through why they can't actually be 1. So the reason it can't be 1 is if C was actually allowed to equal A, then A squared minus B squared equals C squared would end up being essentially that B squared is 0, right? Because A and C would be the same. So if you called both these A squared and solved, you'd get B squared equals 0, which means B is Z, which would mean there'd be, which means B is 0, which would mean there'd be no width, right? Well, if you look at an ellipse, it has to have width, right? It can't just be a line. That would be a degenerate conic. So that's why C can't be equal to A, so you can't have a 1. And the reason that C can't be 0 is if C is 0, then the foci aren't 2 points, right? The foci aren't 2 points. They're the center, right? So they're the center, and it's a circle, right? So they're the center. It's not an ellipse. It's a circle. So the reason that the eccentricity has to be between 0 and 1 exclusively is that an eccentricity of 0, right? Because the only way you get C over A equals 0 is if C is 0. So if C over A were 0, you'd have a circle, not an ellipse. And if C were to be equal to A, you'd have a degenerate, sort of like a line segment, because it wouldn't have any width, so it's not an ellipse. So we're not going to go into eccentricity a lot for our purposes, but if you were to ever go into like astrophysics, or even in just a standard physics class, you were talking about planetary motion. Planets travel in elliptical orbits, not circular orbits, right? So so just to put this in perspective, right? If you were on a planet and your planet is circling a sun, you would much rather that your planet has an orbit that has an eccentricity close to 0, right? Because if you picture it this way, if the sun's in the middle and you're orbiting the sun, right? At no point is your planet crazy close to the sun or crazy far from the sun. If you live on a planet that has an eccentricity for its ellipse that's closer to 1, what's going to happen is if the sun is in the middle, like here, we're just going to put a hot burning sun in the middle, right? So if your planet's here, you're like, cool, nice, sort of temperate all year, a little cold sometimes, a little hot sometimes, I'm all good. But if you live here, right, and this is your sun and you're in an elliptical path that looks like this, you're rotating and you're like, okay, so let's start here. You're like, oh my god, I'm freezing, it's an ice age, I'm gonna die. And then you get here and you're like, oh, the ground is lava. No literal lava, I'm not playing a game, we're all dead. And then, oh my gosh, we're freezing, oh my gosh, we're never gonna be warm again. And then, oh, lava, we're all dead. And then ice age, and then lava, and then you get the point. I mean, it's not really an ice age, but so when we talk about eccentricity, it does start to matter when we talk about like planetary motion and other things like that. But you'll see that more in physics. It doesn't do a whole lot for our class beyond just being a ratio of C over A.